Thank you so much. Recording. Thank you. Thank you so much, Bethany, for that very flattering introduction. And yes, thanks everyone for coming to my Paleoverse talk. I'm really excited to tell you all about this really cool cutting edge method in paleophylogenetics and how you can use my package Paleobuddy to make the most out of it. So let's jump right in. Now, I don't need to tell you that phylogenies are powerful tools in macroevolution, right? If you're interested, for example, in diversification rate estimation, you can use the timing of speciation events to estimate your speciation rate, but it is a little difficult to get reliable estimates of extinction rates from extant-only phylogenies, right? So what we can do, of course, is add fossils to our phylogeny, which preserves our power to estimate that speciation rate, but also increases our power to estimate extinction. So just trying to convince you here that adding fossils to your phylogenies is important in general. From the other side of this coin, for those of us who are really interested in fossils as our main area of inquiry, I'm showing you here a bunch of my favorite canid fossils. We're used to thinking of these as temporal data that can also be used for the estimation of speciation and extinction rates, right? But if you are interested, for example, in traits, how traits might have evolved or how they affected those diversification rates, it would also be really useful to have a phylogeny, right? That hypothesis of the relationship between these species can help us get more investigative power on those lines of inquiry as well. So it would be really nice to be able to put these guys together, right? Have a phylogeny with fossil samples as well. I'm sure many of you are used to this line of questioning, but let's talk about some methods to do that. In an ideal world, if you want to build your fossil phylogeny, you would have all your fossil samples, and for every single one of those samples, you might have your temporal data and your morphological data. If you have extant species in your group, you would also have that for your extant species. Maybe not all of them have fossils, but hopefully you have DNA for all of them. And then, if you're lucky, you might even have DNA for some extinct species. And in this world, you could use this very powerful model called the fossilized birth death, or FBD process, to build your tree. FBD is sort of a spiritual successor of node dating methods, where you would simply use fossils to calibrate your nodes. We call these types of methods tip dating now, where you're actually putting your fossils into your tree explicitly. You're making the fossil samples part of your data, and in that way you obtain a more coherent statistical framework for building your trees with your extant samples, if you have any, your extinct species as fossil tips, or sampled ancestors, which are fossils that have left sampled descendants, and theoretical work has shown that we expect these in a broad range of paleontological parameters. We've come to call this model the fossilized birth death specimen. I'm calling it FBDS here in the screen for you, because of an assumption, or rather the lack of an assumption about the taxonomy of our group. Every single fossil specimen is assumed to be an independent sampling event. This might be an appropriate assumption in some groups of trilobites or dinosaurs, for example, where most species are represented by just one fossil specimen. But in most fossil records, for example, for canids, they're very taxonomy oriented, right? Experts place fossil specimens within species, and then the way this morphological data arrives to us phylogeneticists is attached to the species level rather than the specimen level. So it's really challenging to apply this FBD specimen model to data sets like this. There are workarounds you can do, the most common of which, for example, is taking the entire time between first and last appearance of each of your species as your fossil time uncertainty, okay? But this could lead to some bias because we are ignoring the uncertainty on each end of our range. Maybe instead we could take the ranges themselves as our data unit, right? Stratigraphic ranges are how we call the time between first and last appearance of a given species. So they already explicitly account for the taxonomy that is sort of an assumption made already on the data level for a lot of these fossil records, right? We are able to use all of our uncertainty. We can use the specimen level uncertainty on the ends of our ranges. And we can, of course, also accommodate extant species by extending that range to the present. In this scenario, you could use this very powerful extension of the FBD model called stratigraphic range FBD or SRFBD. It's already set up as a Beast2 package, so you can check it out here, and you can check out the preprint, of which Bethany is a co-author actually, that came out last year, implementing this model in Beast2. And as you can see, the trees that we produce from this model, which we've come to call them stratigraphic range trees or SR trees, you might hear me say that throughout the talk today, have not only our tips, right, but also have these stratigraphic ranges for each of our species that have more than one occurrence. And the trees are conditioned so that every stratigraphic range has to maintain this continuity in just one given branch, right? So we can maintain this taxonomic continuity, we actually need to introduce budding or asymmetric speciation, where a lineage is allowed to continue living after generating a new one. This is a mode of speciation that has been largely ignored in the kind of common statistical methods for building phylogenetic trees in the past, but it's a very common assumption in paleontology, right? And it differs from these bifurcating trees by avoiding this taxonomic breakage that might come from putting two specimens of the same species at different parts of the tree. Of course, this example I'm showing you is kind of a best case scenario, but generally these bifurcating models like FBD specimen could accept tree moves that place these specimens in completely different parts of the tree, which then would be a violation of our data assumptions, right? So the key question of the second chapter of my dissertation and that I'm going to present to you here is, sure, SRFBD might be a more appropriate model for our data. Does that mean it produces more accurate estimates of topology and divergence times than FBD specimen when we apply FBD specimen with that workaround we talked about, right? I got really interested in this question when I was trying to build a phylogenetic tree of canids for application with some comparative methods. So I'll talk to you about my canid analysis, and then my simulation setup was just sort of mirrored on my canid setup. So we'll follow that thread. In terms of my canid analysis, we have 127 extinct and 34 living species. So this is the biggest phylogenetic tree of canids built from scratch to date. We have on average 3 fossil samples per species, showing how, and only 9 of my extant species are lacking fossil samples. So I'm just trying to show you how this is a really well-sampled fossil record, and I think a kind of a model case for the application of this SRFBD model. So much so that a smaller version of this data set was actually used in the preprint that implemented SRFBD. We have, of course, morphological data, just 118 characters, a fairly small morphological data set, and unfortunately that's going to translate into fairly uncertain analysis results. We'll talk about that in a little bit. And then, again, a little bit of a small molecular data set, maybe for those of you used to dealing with phylogenomics, but these are really complex analyses, so we need to be conservative. And we even have DNA for a couple of extinct species, including a very high quality food genome for the direwolf. If you remember all that kind of debacle last year about the direwolf de-extinction and all of that, well, we at least got a really nice high quality genome from it. I'm going to take all of this data and place it into 2 combined evidence analysis on Beast2, an SRFBD one and an FBD specimen one, trying to keep everything as similar as possible to make them comparable. I'm going to focus on the SRFBD results when it comes to canids today. Now, of course, we don't know which of these results are going to be more accurate, and that's where we turn to simulations, right? My simulation setup is as similar as I could make it to my canid setup, just trying to make the results as applicable as possible, just making it a little simpler. And I ran all my simulations on my R package Paleobuddy, which we're going to talk a little bit more about during the tutorial. For these 100 simulations, I again simulated data sets. I again set up 2 combined evidence analysis in Beast2. A lot of computing hours going into this, so a shout out to the HPC infrastructure at ISU. And I'm going to tell you a little bit about my results so we can have a little bit of a shared language about how this model is doing, okay? Here, we're looking at how well these two models are doing at estimating topology, okay? So I'm just showing you when we compare to the true simulated tree, what percentage of our clades in that tree do we see throughout our posterior tree sample? And then I'm averaging that across my 100 simulations, okay? When we compare to the true tree with both first and last occurrences, of course, we can only do that for our SRFBD trees, which output stratigraphic range trees. We see a median of around 70% recovery rate, high variation, but in general, I think pretty good results for a first implementation of the model. When we look compared to the tree with first occurrences only, last occurrences only, or our extant only tree, in all cases, we see similar results, improving with the smaller tree, and in general, a comparable performance between SRFBD and FBD specimen, which again, I think is good news for the newer model. Of course, SRFBD gives us some extra information, and we could ask, how well does it do that, right? Here, what I'm going to show you is, given that we found the correct clade from the true tree, how likely is it that we found the true orientation, meaning which subclade is the ancestral lineage and which is the descendant lineage? If we look at just any speciation node, we have a median right smack at 50%. In other words, if I just gave you the bifurcating tree and asked you to flip a coin and choose the orientation based on that for each node, you would do basically as well, which is bad news, right? But when we restrict our search space a little bit to only look at speciation nodes occurring from within the range of a given species, which I would argue is where we could really expect to detect that orientation, right? Otherwise, we really don't have the data for it. We actually do a little bit better than chance. Only my worst simulations did as bad as chance. We had a median of around 60%, and then the best simulations did around 3/4 of the correct orientation, right? So that's, not perfect, obviously, but I think pretty good news and pretty impressive for, again, a first implementation of this really complex model. Now, when we look at divergence times, unfortunately, the story is a little less happy for SRFBD. When we're looking at FBD specimen, we see, here I'm showing you the mean relative error of divergence time estimates. Whether we are comparing to the first or last occurrence, to the true tree, with first or last occurrences or the extant tree, we see fairly small error between -10 and 10%, centered at 0, which is really good news and honestly really surprising for me. As I told you earlier, I thought that those workarounds would really lead to some bias, and it seems like the model is actually fairly robust to that. So good news for anyone using these models. On SRFBD, on the other hand, we had, regardless of whether we're looking at the true tree with first or last occurrences, with both, or our extant tree, we see a higher magnitude of error and maybe a little more worryingly, a consistent systematic error towards older divergence times. We're consistently finding older divergence times than the truth. Now, let me again point out, this is a very new model. It's a first implementation, and I think we need to do a lot of work to test the method and improve the machinery behind it. But clearly there must be some investigation here, right? I'm on it. Believe me, this is the main reason I haven't published the second chapter of my dissertation yet. So if someone wants to find out what's happening here, believe me, it's me. Right now, my guess it's that this maybe has to do with some tree moves, right? The current SRFBD tree moves were just adapted from FBD specimen moves in Beast2. So maybe we need moves that can better account for those, for that conditioning on stratigraphic ranges being unbroken. That's my guess. Other people I've been talking to have other guesses, and I'm working on investigating all of these threads. But I would also like to point out, even this FBD specimen is a great model for calculating for estimating your divergence times, it still doesn't include budding speciation, right? So there might still be hypotheses that we would like to explore with statistical methods formally that FBD specimens simply can't address, which is why I still, even while we try to figure out why this model the divergence times are not where we want, I'm still going to tell you about my canid results because I think there's some really interesting kinks that we can explore with this budding model. So let me give you a quick little taxonomic primer on canids so we can be on the same page here. Canidae is generally divided into 3 subfamilies. This is all based on this kind of monumental body of work at the late 20th and early 21st century by Wang and Tedford. We have Hesperocyaninae, which is considered paraphyletic because as part of Hesperocyaninae, we have Hesperocyon, a genus that, especially as Hesperocyon, the species Hesperocyon gregarious, is thought to have generated the other 2 subfamilies through budding. The other 2 subfamilies being Borophagiinae and Caninae. Now, all of this is based on parsimony analyses and Wang and Tedford's opinions looking at the morphological data. Of course, they couldn't statistically test this hypothesis because they didn't have access to a model that accommodated for budding speciation, but we do. So let's take a look at our results. Here I'm showing you a maximum clade credibility tree from my canid analysis. I'm going to simplify it a little bit, and I'll point out there's a lot of interesting taxonomic, kind of canid taxonomy things in this tree that I would love to discuss with someone interested in canids, but I'm going to zoom in a little bit on these subfamily level divergences so we can talk about the differences between this and the traditional taxonomic framework of canids and how I think that leads to an interesting discussion about the nature of taxonomy itself. Again, pointing out what the current consensus is, the 2 more recent subfamilies, Borophagiinae and Caninae, kind of as sisters, diverging from the range of Hesperocyon gregarious. We see that in around 38% of our posterior set of trees. What we do see in our MCC tree, however, is this sequential divergence for Borophagiinae and then Caninae from that same range. We see that in around 42% of our trees. And of course, these are different topologies, but I do think it raises an interesting point about taxonomy and about this idea that I'm calling paleontologist taxonomic indecision. I reproduced here for you sort of a consensus tree built by Wang and Tedford in their 2008 book, which is just called Dogs, which I think is really funny. And then I'm sorry, the picture is a little pixelated. I'm trying to use the arrows to help you out here. But we have the range of Hesperocyon, and from that range of Hesperocyon, we have the Borophagiinae and Caninae lineages, and then the rest of Hesperocyoninae all coming through budding speciation, right? So I'm using this to point out that paleontologists have generally agreed, right, that budding speciation is a pervasive phenomenon in the fossil record, and species might last a significant amount of time, enough to generate multiple lineages in some cases, right? But our taxonomic framework is still based on that bifurcating phylogeny view, which kind of constricts species to a discrete point in time. Let me illustrate that a little more with my results. Let's assume, for the sake of argument, that the true evolutionary history of canids is, as we found in our MCC tree, the sequential divergence of the rest of the subfamilies from the range of Hesperocyon gregarious. Because in taxonomy, we force species to be part of only one group, right? And therefore kind of constrict them to a single point in time, we would need to choose some point in our stratigraphic range of Hesperocyon gregarious to assign it to a taxonomic group. Let's say we chose the spot before any of these divergences. We would then get a taxonomic framework very similar to the current consensus in canid systematics, with Hesperocyon being part of Hesperocyoninae and the other 2 subfamilies sister to each other. But of course, we could have taken any other point throughout the range of Hesperocyon and gotten a different taxonomic view. I'm using this to point out that even though paleontologists have generally agreed that budding speciation is a phenomenon that happens, it happens frequently, it will leave significant signal in the fossil record, we still kind of confine ourselves to this view of taxonomy that forces species to one single point in time and, therefore may contradict our budding phylogenetic view of the evolution of these species. And I think that as we expand our methods to allow for budding speciation, we also need to expand our view in taxonomy and start thinking, how can we adapt our concepts in systematics to accommodate this new way of building trees? I don't really have an answer. I have, of course, my ideas and my opinions, but I think this is a big discussion that needs to happen, and I'm really interested to hear everyone's thoughts in the Q&A, or if you want to email me later and chat about this, I'd be very excited to talk about it. A few takeaways I hope you take from this lecture. Using this SRFBD model and explicitly accounting for taxonomy and stratigraphic ranges on our statistical phylogenetics model can lead to accurate topology estimation, including those extra interesting features like the orientation of speciation nodes. But of course, there's some bias in divergence times that need to be investigated, and I guarantee you I'm on that. But still, the biggest takeaway that I want you to take from this talk is that these budding models can lead to new and really exciting hypotheses and questions that make us, really reflect about our philosophies and our concepts in these really interesting ways, right? Specifically, I pointed out the nature of taxonomy here. I'm sure that there's going to be a lot more interesting revolutions that come from us expanding our statistical models and kind of the field walking in tandem with that, expanding our view of things as we go. I'm really excited to be kind of in the cutting edge of this, and I hope I've inspired some of you to also be really interested in these questions. A few acknowledgements. I just wanted to thank my lab and my co-authors, with a special thanks to Graham Slater, my committee member and kind of my canid expert that has gotten me really excited about canids and provided me with this really interesting data set for this model. Ugni Stotz, the first author in the paper that implemented this model. She's been tremendous help in terms of the technical details. And Sasha Gavryushkina, also been a lot of help with trying to help me kind of narrow down where these biases might be coming from, which again, I'll get back to you, but thank you so much to all these people. And with that, I'm going to get into my tutorial here. I'm going to have to focus on just a small part of it because of time, but I'm really excited to tell you all, I'm really excited to tell you all about how to do your first SRFBD analysis, okay? A little overview of how this is going to run. We're going to start in R. We're going to collect our data. I'm using for this tutorial a bit of a smaller version of this canid data set I showed you for my empirical analysis. This is the data set mine was based on, but it was already published in 2015 by Graham Slater, and then it's also used in the Stotz 2025 preprint, which I think makes it a very iconic data set for us to use here. And I know canids are really the only organism group that I can speak like fluently on. So hopefully that translates on the tutorial. We're going to set up our priors and operators and write our beast2 scripts. Those of you who might have experience with beast2 are probably wondering why we don't use beauty. Unfortunately, there is no beauty template for the SRFBD model. I think that's the main obstacle right now to the use of this model, which is why I wrote some custom scripts to try to help out people who might want to use this model and not have to kind of figure out how to use the really complicated XML language in Beast. Then I'm just going to show you how to run these analyses, check for convergence if this is your first Bayesian analysis, and then aggregate results and build your tree summaries, all that good stuff. Now, if I had an hour to give you this tutorial, I would go in detail in every single one of these steps. And I'm hoping that my written tutorial and my custom scripts are commented well enough that you would be able to follow these steps and adapt these analysis to your data. Unfortunately, we only have around 20 minutes here. So what I'm going to be focused in is once you've run your analysis, we were going to look at the results, right? We're going to read those results in R, look at parameter estimates, and then, and this will be my main focus of the tutorial today, evaluate the topology and divergence times in your results based on your posterior sample of trees. And we're going to do this with our R package, again, paleobuddy, which we have a lot of really exciting functions implemented there to help you go through your budding phylogenetic tree sample. So let me share again really quickly so I can show you. So again, this is my website. The organizers have dropped a link on the chat for you to follow along. I'm gonna zoom in just to make it easier to see. Please let me know if there's trouble seeing all of this. And I'll mention when you're going through this in your own time, hopefully, if you would like to use our markdown, instead, you can download it here, okay? Because I built this within our markdown, so. And again, I'm going to, just for the sake of time, I'm going to have to go, not focus on the inference and the setup side of things here. I'll just point out, unfortunately, we haven't had the time yet to polish everything and put all of these new exciting developments for paleobuddy in CRAN. The version of paleobuddy in CRAN right now has kind of the core functionality of simulating birth, death, and fossil samples and building bifurcating phylogenies, I should say, and doing all that good stuff that hopefully you find interesting. But this kind of budding phylogeny stuff right now is in the development branch. So I'm showing you here how to download that branch specifically. Once you have all that set up, you would write your Beast2 scripts. Again, I hope that the custom scripts that I wrote are well commented enough that you're able to adapt it to your data. Please don't hesitate to contact me if I could help you set up, if there's something here that's not clear, or if I haven't accounted for some Beast2 functionality that you would like to use. I'm very happy to help you work on this. Figuring out how to write XMLs is a pain, and I hope that my suffering translates into you not having to suffer in your turn. But we're going to again assume that we ran all of our analysis, we assessed for convergence, and then aggregated all of our results, including building a maximum clade credibility tree. And this tree, I show you here how to plot it in ICTree, which is a browser tool that is currently, aside from paleobuddy, the only possible tool to plot budding phylogenies right now. Okay, not only budding phylogenies, but again, stratigraphic range ones. You can color your branches by the stratigraphic range, as you can see here. And I'm going to be showing you this tree occasionally, which is the MCC tree from my own canid results, because we're going to use it to kind of find interesting nodes to explore with paleobuddy. Okay, so I'm showing you how to plot it here. We're able to plot budding trees in paleobuddy, but if you've ever tried to plot phylogenies in R, you know it's a bit of a pain, and the plot window is always, it's weird. I always prefer to plot in IC3 where possible. When you're going through this tutorial, if you don't want to wait for all these analyses to run, because they do take a few days, you can feel free to download the results files from my own analysis here and follow along. I'm not going to linger too much on parameter estimates. If you've ever done any kind of birth-death analyses, you've already looked at this kind of source, and you can obviously take a look at the text on my tutorial as well. I'm going to focus more on the topology side of things, which I think is where our new tools in paleobuddy really shine. So if you've ever dealt with phylogenies in R, you've probably definitely used this package called ape. I call it APE, and my friends make fun of me for that. And ape is really useful, really powerful. It creates this object called a phylo object, which holds your phylogeny. And every package in the field that deals with phylogenies goes through ape somehow, right? Unfortunately, ape doesn't preserve node comments. So if I want to tell on my tree which clade here is a descendant and which is an ancestor, the way that the Beast2 folks have decided to do that, which I think is probably the most obvious way to do it, is to have an orientation comment on your on each node, right? Telling you whether your node is an ancestor or a descendant. And that's how we can set things up here. So we need to preserve node comments. I explored a bunch of different solutions for this, and then we kind of settled into building our own object that we called bud phylo, which hopefully will be, kind of easy to convert between bud philo and philo objects, so you don't lose your ape functionality. But then this object is a little bit more expensive, and it is able to contain all of the information that we need to deal with these budding trees. It's simply a data frame where each row is a branch of your phylogeny, and therefore the node at the end of that branch. Each column is information on that branch or node, for example, the orientation, the parent of a given node, the length of the branch, etc. Because we built this with the beast2 output in mind, this also takes explicitly accounts for stratigraphic range trees where, sorry, let me just hide my meeting controls here. Stratigraphic range trees where not only do we have budding speciation, but we also have our stratigraphic ranges, right? So that each species with more than one sample has a first and a last occurrence in our tree. So each species sort of has, may have at least two tips, right? And we account for that so that this model our object can differentiate between the occurrence, right? First or last, and the species in which that occurrence is. Hopefully this is enough detail about bud philo. Again, please feel free to ask me questions on the Q&A. So back to the tutorial here, we can read our trees with our custom read nexus file. We could also function. We could also read pure Newick files if you would like. And then we come to the point where we have our tree sample and we would like to analyze our results, right? So what I'm going to do here is I'm going to point out a couple of interesting nodes in our MCC tree, and then we're going to ask the question, how often does that happen? Okay. For example, I am sure you know about the gray wolf, right? These great guys right here, we see in our tree, we have directly budding off of the range of the gray wolf, what I'm calling the direwolf species complex. So the direwolf and its close relative Armbrusterized wolf. I'm not going to discuss how close to correct this is, or, you know, we're not going to talk about canid taxonomy deeply here. I will point out this is a morphological only data set. So if you've heard about other topologies involving the direwolf, remember this doesn't include DNA. But I'm just using it to illustrate, if you have this result, you might ask the question, how often do we see exactly this situation, right? The direwolf complex budding off directly from the range of the gray wolf. To answer that question, I wrote a custom function here that uses a bunch of functions I want to illustrate for you that we implemented in Paleobuddy. Most of these are sort of extensions of APE functions or kind of tangential packages that deal with these phylogenies, and we just want to make them work for bud philo objects. And, you know, when we see an improvement that we would like to make, we make it. So we have a function here to ask how whether a certain group of occurrences is monophyletic in our tree, get the node representing the most recent common ancestor of that group of occurrences, get the descendants of a given node in our tree, and then get the immediate children, the two nodes that are immediate children of a given node in our tree. And this function is really where we would get that orientation information as names of each of the children nodes on the output, okay? So I'm not going to walk in detail through that function, but you might imagine how we're going to do this, right? We would check that all the direwolf and Armbrusterized wolf occurrences are monophyletic. We would check that they are monophyletic with the last gray wolf occurrence, and we would check then that this clade is the descendant of a given speciation node. So doing that and applying it to all of the trees in our posterior sample, how often do we find it? Well, it seems like that exact situation occurs around 27-28% of our posterior sample of trees, okay? When I saw this, and then I compared to the node comments at our actual tree here, you might notice it says posterior probability 0.418, right? So that might lead to some questions here. And the reason is, in these posterior node comments, we are including the situation where this clade buds off not directly from the range of lupus, but from the lineage leading to that range. So you can imagine if this speciation was occurring here, for example, right? So just to make sure that we are accounting for everything correctly, I added a little argument to that function to check that exactly that situation. And we see that it happens at around 14%. And you can do your math here and see that this is going to add up to around 41, almost 42% of our trees, right? Again, pointing out this is a fairly low posterior probability, right? This is a fairly uncertain data set, unfortunately. And I'm hoping in my postdoc to expand that morphological data set so we can learn, get more certain results about canids in these sorts of analyses. But I hope this is, just a nice illustration of how we would do this kind of analysis with Paleobuddy. A second example I wanted to point out, which I think is going to be very interesting in showing you the power of these stratigraphic range trees. We're going to zoom in on the same kind of high-level divergences that I talked a little bit about in my taxonomy discussion. So as you can see, it's a little different, the order of the subfamilies, but it does the same thing that happened in our lecture happened here, where each divergence, every single other group outside of Hesperocyon and Gregarious seems to diverge from the range of Gregarious, right? And again, you might ask, how often does that happen? There's a lot of different little possibilities you need to account for when you're dealing with tree topologies and asking these kinds of questions, right? But because these are stratigraphic range trees, I want to show you how we can narrow down our search space a little bit, right? So the first thing we're going to do is we're going to create a clade that has every single occurrence of in our data set except for the first occurrence of Gregarious, right? And we're going to ask, is it monophyletic? Because this is what's happening in our MCC tree. And this seems to happen in around 41% of our posterior trees, okay? Now, of course, that doesn't tell you exactly whether it is this situation, right? There might be situations where the last occurrence of Gregarious is monophyletic with the rest of the occurrences that are more complicated than just this, right? But the interesting thing you need to remember is these SR trees are conditioned on the stratigraphic range remaining one unbroken lineage in our branch, right? So this really narrows us down to at least only two possibilities for this 41% of trees. Either this happens where every lineage buds off of the range of Gregarious, or they might bud off at a different order, right? Maybe Gregarious ends here and we have another other kind of divergences, but clearly some divergences at least would happen from the range of Gregarious. Or we have the entire range of Gregarious before every other divergence, right? And we still would get that same result regarding the monophyly. But because we are using the structure of these SR trees to narrow down our possibilities, we only need to test one more possibility, right? Which is that every single occurrence, except for both Gregarious occurrences, is a monophyletic group. And we get around 1% of our trees show us this clade. In other words, we can be sure that in around 40% of our trees, we have the range of Gregarious and a bunch of divergences from that range, with Hesperocyon Gregarious first, that node being a sampled ancestor to every other occurrence in our data set. Okay, so again, fairly uncertain result. Don't go taking any big kind of canid taxonomy results from here. But I just want to point out some interesting things we can do using these functions from Paleobuddy and the structure of these budding stratigraphic range trees to our benefit. I have a little portion in the tutorial here looking at divergence times. Of course, the difference between looking at divergence times in bifurcating trees and budding trees is just a difference of knowing which function to use, which is why I'm showing you the code here. And you can, of course, run this when you have the time. But there's no very conceptual difference about these divergence times, so I'm not going to linger here, okay? I'm just going to give you one final example, because I want to point out, of course, these little examples that I've been giving you, right? Just checking on time here, okay? These little examples that I've been giving you are interesting, and they might be the kind of thing that you write on the body of your results or discussion section on a paper using this model. But anytime you're running these analyses and you get these huge posterior sets of trees, you must have some systematic way of investigating the clades in that tree and their relative frequencies. And I started writing this function that I'm calling extract.clades for my own kind of use with my k-NIT analyses. And I realized that maybe it would be something useful to have on Paleobuddy, kind of giving this next level, right? Where not only are we investigating like questions about a single tree, but a set of trees and, specifically a set of clades in a set of trees, right? How does this function work? You give it a tree, you give it options on whether you want to look at orientation and sampled ancestors as well. And what you get back is a list of clades organized as you see here, with occurrences separated by commas, and then a little field for, which part of this clade might be the ancestor lineage, or if this is a sampled ancestor node, which species might be a sampled ancestor, right? So this is a very efficient way to list out all the clades in your trees. I might expand this tutorial in the future to kind of show, kind of take this another level and show, okay, how do we do this for every single tree? How do we organize this nicely, right? I have some code for that on my second chapter. So once that's published, I can kind of reuse that. But I hope it's clear how you would just apply this to a set of trees, and then you have a very efficient way to compare the relative frequency of clades, including considering orientation and sampled ancestry, right? And with that, this is all I have for you for our tutorial. I hope my lecture has kind of excited you about these really fun new methods and the kind of new ways they must make us think within our biases in our field, and that this tutorial seems useful for you, and it's been, hopefully enough to make you interested in trying out this model. And again, please, if you're interested, go through this on your own time and let me know if there's any way that I can improve it, any way that I can help you set up your data. I'm very friendly, so please feel free to reach out. Okay, and with that, I would just like to thank all of you for coming to watch my lecture, and thank the Paleoverse organizers for inviting me here. It's been really fun to prepare this, and yeah, I would take any questions.